plate tectonics, and in this presentation our main concern will be an explanation of science and prediction. So particularly our real life situation is on December 26, 2004, there was a great earthquake that happened in Sumatra, Adman. Actually, scientists didn't predict the event would occur because due to the theory, the area was believed to be immune to such giant earthquakes. And hence, this made scientists rethink the theory of plate tectonics. So what was the theory? The theory says that giant earthquake occurred in first year subduction zone. However, this incident happened in middle age and slowly moving plate subduction zone. So this is how the contradiction happened. So here is the map. As we can see on the map, the Indian plate is a middle age and slowly moving plate, and it is subducted into Burma microplate, which causes a stress along this area, which is colored red. And this is a middle, as I said, this is a middle age and slowly moving plate where the giant earthquake happened. So the knowledge issue that we extracted from our real life situation is to what extent does prediction test the validity of a scientific theory? So what is a scientific theory? Scientific theory is a well-supported body of interconnected statements that explains observation and can be used to make testable prediction. But in everyday use scientific theory, it means a hunch or a guess, but which needs a proof. But however, in science, a scientific theory is not a guess or a hunch. It is a well-sustained, well-supported, and well-documented explanation for our observation. So what are the roles that scientific theory plays? There are great roles that scientific theory plays for making prediction. Also, we use scientific theory as an explanatory powers. And so, since we are concerned as scientific theory is one of the qualities of the scientific theory is making prediction. So we have to see what are the bases in making prediction, so that we will be able, in order to see the role of scientific theory as prediction. So prediction are based upon a careful analysis of patterns, which are essentially recurring events. And patterns can be found in the natural sense, in the human sense, which we shall see later in our presentation. And the key to be recognized patterns can provide the basis for us to later make prediction based on our observation of the repetition of the patterns, and then making a subsequent prediction based on the data. So the more patterns we observe, the more our prediction will be stronger. So we will assess different areas of knowledge, and we will see the role of prediction in validating a scientific theory. And also, we will discuss different theories, and the theories that will be considered in this presentation are plate tectonics, evolution by natural selection, valence shell, electron pair repulsion theory, and flip scale. And Enoch will take you through the natural sense.
The theory of plate tectonics is one of the theories that we observe patterns most of the time. And due to historical approach, most of the earthquakes and volcanic eruptions occurred in the fast young subduction zones. And this pattern has been observed for several years. So scientists are able to predict from this pattern what will happen in the fast and young subduction zones. As we can see from this map, the giant earthquakes happen in plate boundaries, which is the fast and the young subduction zones, and these are marked by a red color, and scientists are able to predict from this pattern what will happen. And what will be the extent of the earthquake. However, the theory of plate tectonics doesn't seem to predict the exact time of when the earthquake likely to occur. However, if you see the study of astronomy, an astronomer can predict exactly when and where the eclipse likely to happen. This is due to the fact that the state or the advancement of technology is too sophisticated and aid astronomers to observe accurately what is going on the space, and having sufficient data help astronomers to observe what is going on the space too. So when it comes to the strengths of the theories, normally the theory able to predict places with giant earthquakes and volcanic eruptions likely to happen. This is because the scientists use reasoning to make a correlation between the giant earthquakes and the places where the giant earthquakes occur. And also it provides a mechanism to explain the continental drift theory. In science is based on more than an empirical observation, and scientists need to explain what they have observed. And the continental drift theory doesn't seem to explain the mechanism for the movement of the continents. So another theory was needed to explain the mechanism for the movement of the theory. So the further data led to the development of the plate tectonics theory, which explained the mechanism for the movement of the continents. Moreover, it enables to predict the magnitude of the earthquakes, volcans, or tsunamis. Even though the theory is able to predict this, where the giant earthquakes likely to happen, it failed to predict the giant earthquake which happened in Sumatra. And this will lead us to talk about the weaknesses of the plate tectonics theory. Before I talk about the weakness of plate tectonics theory, I would like to say these are the possible areas of weaknesses that we repeatedly considered in our presentation. The first weakness of the plate tectonic theory is sometimes it's impossible to experiment. This will limit the amount of data that could test the theory. However, in natural sciences, most predictions are experimented. So as to have sufficient data. When it comes to the conclusion part of the theory, the conclusion part seems provisional, and this is due to inductive reasoning of reasoning, and scientists generalize that giant earthquakes occur in a fast young subduction zones, but the situation presented in the real life situation falsifies this generalization, and this generalization arises from this way of reasoning tend to ignore some exceptional which question the strengths of the theory. And the lack of advanced technology also limited scientists not to predict this particular event. Before this particular event, the scientists used seismometers to detect where the giant earthquakes likely to happen. However, after this particular event, they used advanced technology in order to evaluate this giant earthquake, and they took advantage of new technologies incorporated with a range of new techniques. This gives a better picture of what happened on the fault. So, what is the implication of this particular event on the theory? First and foremost, it makes scientists to rethink their theory based on the data collected after this particular earthquake. Also, it makes to re-examine some of the pre-December 2004 assumptions scientists made about such rare events. Some of these assumptions were giant earthquakes occur only in a fast young subduction zones. Malcolm will take us to evolution.
Yeah, evolutionary theory is one of the scientific theories that we have in a current generation that explains the origin of life and the development of life in geological time. As Henok explained, some sciences use historical approach towards solving some scientific problem. Historical approach is the use of historical data or patterns of the past to explain the situations and to enable us to predict what will happen in the future. So, like theory of plate tectonic, the theory of evolution also uses historical data to solve some of the problems and to explain the origin of life. This means most of the time we use archaeological evidences to support our explanation. For the sake of this presentation, even if there are a lot of arguments that come along the theory of evolution, I'm particularly interested in the fact that the theory of evolution has been tried to be falsified due to the fact that it cannot make testable predictions. I shall assess some strengths of the theory, then I'll look at some weaknesses that make it difficult for evolutionary biologists to make predictions. When it comes to the strength of the theory, evolutionary theory is very strong in terms of explanation of origin of life and the changes that happen in the psychological and physical behavior of species over the geological time. At least in current times, is the single scientific theory that we have in the scientific community to explain these things. So, besides the theory of evolution uses some strong evidences that support its explanation. For example, fossil records, homologous anatomical structures, and artificial selection also help to explain what needs to be explained in terms of the theory of evolution. And especially artificial selection is what's trying to alleviate the problem of experimentation when it comes to the weakness of the theory. For example, some of the weakness of the theory of evolution is that it cannot make a testable prediction, and this is due to the fact that it's difficult to have a simple falsifiable hypothesis that could be falsified by experimentation. And this is due to the fact that when the theory itself explains the changes in physical and psychological behavior of species, the changes occur for millions, even 10,000 and 100,000 years. So it's difficult to conduct a laboratory experiment and to observe such changes. So this makes it very difficult to conduct an experiment to have a large amount of data that will explain the theory. Another problem is that the variables we need to consider are very complex, and these variables also interact to make some changes that we didn't predict. Specifically, these variables in the theory of evolution are very sensitive to to changes, and so a specific prediction about, for example, what mutation will occur and what traits will survive are very impractical in the theory of evolution, as Rowan explained it. Besides, when we look at the initial condition to make it clear, we need to have a clear idea of the effect of all these initial conditions. For example, gene mutations, experimental, environmental effects such as food availability, predator effect, weather condition, and gene combination. So it's very difficult to have a clear idea, for example, the effect of food availability on the phenotypic characteristic of an organism. In gene combination, for example, for human, there are over, until now, an estimated number of genes is around 10,000 and around 100,000, sorry for that. And there is a gene combination. It's difficult to trace all these combinations and to have a clear idea of what behavior we will observe about this. So this makes it very difficult to predict in terms of the theory of evolution. So scientists argued that even if the theory of evolution is not able to predict, it's likely that every scientific theory needs to eliminate some irrelevant factor in order to make prediction in the future, because in every science there are a lot of variables we need to consider. So it's very essential to eliminate some irrelevant factors in order to make prediction. And this is a difficulty for both human scientists and evolutionary biologists, as we shall see later in case of human scientists. Now Manatu will take us to the chemistry.
Okay, I'm going to talk about the kind of prediction in chemistry. So before I talk the kind of prediction in chemistry, let me make this point. When we see that kind of situation in chemistry, the situations doesn't change. As in, for example, if you see the carbon atom that existed before 2,000 years ago, it is the same carbon atom that we can see right now. But when you consider history, societies change and the ideology also changes. And that makes it difficult to talk about prediction in history. Also, as Malcolm talked about in evolution, it's a long process and it changes. So it will be difficult also to talk about the predictions. So the same thing happens in plate tectonics as it uses a historical approach. So let me talk about the pattern that exists in chemistry. What is periodicity? Periodicity refers to the repeating pattern of physical and chemical properties that is seen at regular interval in the periodic table. This is a common, a familiar concept that we discussed in our class. So the existence of this pattern enable some chemists in order to make prediction. For example, if you see this periodic table, Dimitri-Mendeleev periodic table, Mendeleev was able in order to predict by looking at the patterns using the atomic mass number, and thus he left some spaces as we can see in his periodic table. So he predicted the discovery of new elements, and here we can appreciate the use of deductive reasoning. So let us consider one of the theory that we have in chemistry and the ability also to predict, and I shall discuss some of the strengths and the weakness of this theory. So what is valence electron pair repulsion theory? This theory mainly involves predicting layout of electron pairs surrounding one or more central atoms in a molecule, which are bonded to two or more other atoms. The geometry of these central atoms in turn determines the geometry of the larger core. It's also a model in chemistry used to predict the shape of individual molecules based upon the extent of electron pair electrostatic repulsion. For example, if you see CF4, it is a tetrahedral shape because here the central atom is carbon, and hence carbon has a 4 valence electrons. And using the central atom, using the valence shell electron of the central atom, we can determine the geometrical structure of the compound. So what are the strengths of the theory? The strengths of the theory is it plays a great role in predicting the structure of a compound by looking at the geometrical structure of the central atom and using the valence shell electron. As I told you, I've given an example, CF4, which is a tetrahedral shape. And also to determine the melting and the boiling point of a compound. For example, if this is H2 is a V-shaped molecule, is also an example for the kind of the structure that H2O has. And also for the melting and boiling point, for example, H2O has a high boiling point and melting point. This is because due to the kind of the bonding structure that, the kind of the bond that H2O has. Since H2O has a bond between oxygen and hydrogen, that is a hydrogen bonding. And hence, this will make H2O to have a high boiling and melting point. So, Henok has discussed some of the possible areas of weakness of theories in general. Has discussed the impossibility to experiment and the danger of overgeneralization, problem of reduction, obtaining precise prior knowledge, measurement difficulties, influence observer effect, and uncertainty principle, which we shall see later, and complexity and interacting variable. So what are the weaknesses in this particular theory? So the weaknesses in this particular theory is it is qualitative, and hence we cannot talk about the quantitative property of the compound. For instance, we cannot determine the exact degree of repulsion between each bonds, because since it is qualitative, the data collection is a qualitative, it will make difficult for us to talk about the quantitative properties of the compounds. And also, this theory cannot apply to all compounds. For instance, benzene is exceptional to the rule. So this is one of the weaknesses we have seen, overgeneralization. And it's because if you see the kind of the pi bonds in benzene, it's evenly distributed. So it will be difficult for us to talk about the valence shell electron pair repulsion theory here. So we have to see the scientific method in order to clarify the weakness of the theory. So this is just a typical scientific method, and it might not be always followed in this way. So is it due to the hypothesis, or due to the experimentation, or is it due to the observation, or due to the data collection, or is it due to the conclusion? So in this case, we'll be interested to talk about the data collection, because as I told you, the data collected is only qualitative. So this would be difficult to talk about the quantitative properties of the compounds. And so why aren't we able to measure the exact degree of repulsion between the compounds? So I'll talk about the uncertainty principle. So this, which was it was by Heisenberg, and this principle states that it is impossible to know the exact position and momentum of an electron, as momentum is related to time. But what this implies is that it is impossible to know the exact location of an electron at an exact momentum in time. The more precisely the location is known, the less precisely the time is known, and vice versa. Heisenberg principle applies to any particle with mass, but the more massive, the less the uncertainty of the particle. So since this principle enables scientists in order to make prediction, scientists use some kind of probability in order to use. Since it is difficult to measure the exact momentum and location simultaneously, scientists use some probability. They use that, maybe the electron is located somewhere, like they use, most probably the electron is located around here. So scientists are using as a base where there is high probability that electrons are located in order to make prediction. And also, this applies to the whole of the physical universe. For example, in describing the three-dimensional shapes of the atomic weight, there is a high probability that electrons are located as they use it in quantum mechanics. And we know that there are px and py and pz suborbitals, and we assume that there is equal probability of electron being located at each suborbitals. And also there are some assumptions that are used in this theory, where we consider like triple bond and double bonds as a single bond. So why can't we measure the exact location and momentum at the same time? Also, this will lead us to talk about the problem of observer effect. In order to explain what is observer effect, let me give you a very simple example that we experienced in our class experiment. For example, when we want to measure a certain sample using a thermometer, the thermometer itself has its own temperature value, and hence the temperature value of the thermometer will interact with the temperature value of the sample, and hence this will alter the final reading of the sample. So this also happens in subatomic level, as the physicist measuring device interact with what is measuring on subatomic level. And so, Malcolm will take
like the natural scientists, human science also construct and propose a scientific theory that will later be used to explain some situations or behavior of human beings, and also they are used to predict how humans behave in the future. So let's first assess why human beings are able, why social scientists are able to predict. Human scientists are able to predict. Basically, they use an advantage of the law of large number. The law of large number explains that as we assess a larger number of people, as the number of people get larger, the probability of the exceptional behaviors affecting our data is getting low. For example, in economics, we assume that all consumers or producers are rational, but this may not be true because there are some exceptions to the rule. But as the number of people is getting larger, the effect of these exceptionals or the effect of irrationals affecting the final data is very low. So this explains why human science are sometimes able to predict exactly what will happen in the future. Besides the reasoning, like natural scientists enable human scientists to establish a relationship between particular experience and a more broadly general ones within the world that they perceive. This helps us to get an evidence which can then be associate the causes and effects and make correlation which later be used to predict in the future. Besides, understanding of patterns also allow human scientists to predict, as I will use the Phillips curve to explain how understanding of pattern enables to construct a relationship between rate of unemployment and inflation. Human scientists, like natural scientists, sometimes find it difficult to predict. When we look at why human scientists find it difficult to sometimes have an exact prediction of what will happen in the future, I come across the following pointers. Sometimes it's almost in human scientists, it's very difficult to carry out a controlled laboratory experiment. And this will not enable us to have a large amount of data that will later be used to explain some events or situations which will later be used to predict. Besides, there are too many variables. This is what we call complexity of variables that may cause a larger changes in the future which are unpredicted. Even some observations are biased due to the prior knowledge we have about human behaviors. Besides, sometimes individual behaviors are also unpredictable, and the baseline assumptions, that means the very basic assumptions we use in human science are very subject to change, and this is a limitation for human scientists in terms of prediction. But Milton Friedman tried to argue that it doesn't matter that the assumptions are wrong as long as one can extract a general rule from which one can make prediction. When I read this thing, I was not arguing with the statement, because like I said, some of the assumptions may be wrong, as humans are rational, or consumers and producers are rational. But as the number of people we assess is getting larger, the effect of these irrational people on our data is getting low. So as we can extract a general rule from human behavior, this may not, the baseline assumptions may not affect our final data. And another problem is that sometimes the predictions are based on extrapolation of data well beyond what is reasonable. So these are some of the problems human scientists face when we try to apply the scientific method to human sciences. Let's say an example of the Phillips curve, why human scientists find it difficult to predict. Using the pattern that is observed for a long period of time, a scientist called Phillips was able to establish a relationship between unemployment and inflation. And the explanation behind this relationship is very reasonable, supported by evidence. For example, as people are getting employed, they get more money. When they get more money, they tend to demand a lot, and they will buy a lot of things. This will insist the producers to increase the price, and his increase in price is called inflation. It looks very reasonable explanation that's provided behind the Phillips curve. But in 1970, some exceptional situation occurs. Over the 1970s, what occurred was inflation and unemployment rose together. This could not be explained using the Phillips curve. So as we saw throughout this presentation, there are some exceptional that are very strong to question our theories, and these exceptionals are what are making our prediction based on our theories very difficult. So when we look at some explanations behind why human scientists are very difficult, we come across the butterfly effect. The butterfly effect is a philosophical term that is used to explain why human scientists find it difficult. For example, prediction of the behavior of any large system is virtually impossible unless one accounts for all tiny variables. I think this applies to all scientists which has a complex and large amount of variables. As we saw in evolution, we need to have a clear idea of all initial conditions and variables in order to predict. So these variables which we suppose or we consider irrelevant may have a larger effect in the dynamic system in the future. And another philosophical term I come across is the Cassandra paradox. This explains an interaction between the social investigator and what's being investigated. It's like the phenomena here is like the observer effect. The social scientist or the one who is predicting may influence the behavior of the person, and the person may tend to behave in order to defy that prediction. And this is what's making prediction very difficult, even if our theories are very strong. After this, Henok will take us to the implication of what we talk on the theory of detection.
Okay. We will come back to our real life situation. we would like to assess the implication of the theory of plate tectonics. In the theory of plate tectonics, there are things scientists can't really measure, but these variables may cause and predict effects. For instance, exact measurement of the speed was difficult to know. The initial calculation that it was a 9 earthquake didn't take into account what scientists call a slow sleep. This slow sleep is the silent and the slow movement of an earthquake, and this movement doesn't show up in the seismometers. That's why scientists find it difficult to measure the exact magnitude of this particular earthquake. So what happened on this particular event is the slow sleep movement, where the fault is delimited by aftershock shifted more slowly, and this additional energy released by slow sleep along the fault played a key role in generating a devastating tsunami, and such kind of situation is known as a butterfly effect, as Malcolm said it earlier. So Malak will conclude our presentation.
So, in conclusion, I would like to say in our presentation, we have talked about the role of prediction validity in scientific theory. As we have seen from the 2004 tsunami incident, how theories sometimes fail to predict. And also, we have seen like there was a mismatch between theory of plate tectonics and 2004 tsunami, where the real life situation, as we have seen, the giant earthquake happened in slowly moving and middle age subduction zone. But scientists' theory said that the giant earthquake happens in young and fast subduction zone. So also we have seen as an explanation for why our theories sometimes are less accurate. For example, the uncertainty principle and the observer effect. Also, we have seen the different approaches that some theories use, as for example, evolutionary and theory of plate tectonic use historical approach, whereas the valence shell electron pair repulsion theory uses an experimental approach. And also, we have seen the role of prediction in validating a scientific theory as one of the qualities, but it's not only prediction which is used in order to validate a scientific theory. There are also other qualities that validate the scientific theory, such as explanatory powers. Thank you for your attention.